Dear friends, welcome to a lecture on complex analysis. In this lecture, we shall study some properties of moduli of complex number and some problems also we shall solve. In our earlier lecture, we have defined modulus and conjugate of a complex number. You please refer that lecture. I have written in brief the revision that we have studied in our last lecture, that is definition for modulus and conjugate, and some properties of conjugate we have studied in our earlier lecture, because we are going to use these same properties to prove certain properties of moduli. If complex number is z is equal to x plus iy, then the modulus of z is denoted by mod z and is defined as under root of positive square root of x square plus y square. And conjugate of z is denoted by z bar, it is x minus I into I. And these properties we have proved in our earlier lecture. Double conjugate of z is equal to z, mod of z bar is equal to mod of z. This is a correction. Absolute value of z bar is equal to the absolute value of z, because absolute value is defined as like this. So what will be mod of z bar? Mod of z bar will be this modulus of this, which will be again under root of x square plus minus y whole square, but minus y whole square is same as y square. Therefore, modulus of z is equal to modulus of z bar. And next is the conjugate of z1 plus z2 is equal to sum of conjugates of z1 and z2, that is conjugate of z1 plus conjugate of z2. For product, conjugate of z1 z2 is equal to conjugate z1 into conjugate z2, and similar property for division holds. Also we have proved real z is z1 plus z bar divided by 2, imaginary z is z minus z bar divided by 2i, and the last property is also important, z into z bar, the product of these two, z and z bar, is, you can see x square, it is x square plus y square, which is mod z square. So these are some simple properties that we have proved in our earlier lecture. Now we shall consider properties of moduli. The first property we shall have for moduli is mod of. See, we shall consider here as the properties for moduli, and that we can write as mod of z1 into z2. z1 z2, mod z1 z2 is equal to mod of z1 into mod of z2. So this is the first property that we shall prove, and to prove this property we shall make use of this last relation, last property of conjugate, that is z bar is equal to mod z whole square, and we will now write its proof. See, we have mod of z1 z2 whole square, this is equal to, in the left side we have, it is z into conjugate of z. So instead of z, it is z1 into z2. So this will be z1 z2 into conjugate of z1 z2, using this last property, since mod z square is equal to z into z bar. And now this is equal to z1 z2. See, conjugate of z1 into z2, we have this property here, conjugate of z1 z2 is conjugate of z1 into conjugate of z2. And further this can be written as, we shall write z1 into z1 bar. Multiplication is commutative as well as associative, and therefore we can write like this, z2 into conjugate of z2, these two together. And again, what is this product? z1 into z1 bar z bar is mod z whole square, and therefore this is mod z1 square and this is mod z2 square. The left side is mod z1 z2 whole square. Now we shall take the square root on both sides, and we know that the absolute value is always positive. So therefore, taking square root and modulus or absolute value is never negative. So we don't consider the negative sign for square root. We get mod of z1 to z2 is equal to mod z1 mod z2, and this proves the first property. Now we shall consider the second one. So this is for product. We now write for quotient. Mod of z1 by z2, z1 divided by z2 is equal to mod z1 divided by mod z2, and here the condition is z2 is not equal to 0. See, we can use the same property, last one, that is this, and we write the square of this. Square of z1 modulus of z1 z by z2, square of modulus z1 divided by z2 is equal to z1 divided by z2 into conjugate of z1 divided by z2. See, in reverse way, square of mod z is z into z bar, and this can be written as z1. Now we know that this conjugate of z1 by z2 is written as conjugate of z1 divided by conjugate of z2, and therefore this can be written as z1 conjugate of z1 divided by conjugate of z2. Now see, the numerator is z1 into z1 bar and the denominator is z2 into z2 bar, and thus this is again by the property, last one is z bar is mod z square. So this is mod z1 square divided by mod z2 square, and the left side is mod of z1 by z2 whole square. So taking square root and noting that the absolute value is never negative, we get, so thus this gives z1 by z2, mod of z1 by z2 is equal to mod z1 divided by mod z2, taking square root. This proves the second property. Now we shall consider the third property, which is important, and that is also known as triangle inequality. And the property is mod of z1 plus z2 is less than or equal to mod of z1 plus mod of z2. Now to prove this property, we shall start with the same result, last result that we have written here, and we have used in earlier two properties. So proof for this is, we have square of this z1 plus z2, mod z1 plus z2 square. This is equal to z1 plus z2 into conjugate of z1 plus z2 by this property, and this further is written as z1 plus z2 into conjugate of Z1 plus conjugate of Z2, this property, see. And this now the product is to be written as Z1 Z1 bar plus I shall write Z1 Z2 bar conjugate of Z2, and then the product with Z2 Z1 bar, but that I shall write Z1 bar Z2, the product is commutative, so this I have written like this, and the last is Z2 into conjugate of Z2, and this is equal to further Z1 bar by this is mod Z1 square, mod Z1 whole square, and these two terms we shall write like this, plus Z1 Z2 bar plus Z1 Z2 bar and its conjugate plus Z2 mod Z2 square. Now you note this, see, conjugate of Z1 into conjugate Z2, and that is by this the property, see this one, conjugate of Z1 into conjugate of Z2, and using this double conjugate is Z, so this will be Z1 bar and double conjugate of Z2 is Z2. So therefore we have written like this, and again this is equal to, now see, this is mod Z1 square plus, now what is this sum, you note this is as it is and these two are equal. Now what is Z1 bar plus conjugate of Z1 bar Z2 bar, so that is that means the result is like this, Z plus Z bar. So this instead of Z here is Z1 Z2 bar, this complex number plus its conjugate, a complex number plus its conjugate is 2 times real part of the complex number, and therefore this will be 2 times real part of which complex number, that is Z1 Z2 bar. This sum is like this, and this is plus Z2 mod Z2 square. So using this result, since Z plus Z bar is equal to twice real Z, it is very obvious to verify the result, and we have proved it in our earlier lecture. Now further, what is real Z2 bar, real part of this, and we have the property of modulus, that is the real Z. So what is the real Z? Real Z is, if Z is this one, what is real Z is X, and X is always less than or equal to under root of X square plus Y square, because when Y is 0 then these will be equal taking positive quantity, and if Y is non-zero then this is always greater. So therefore X is always less than or equal to this means, but what is this? This is equal to mod Z, and that means the property is real Z is always less than or equal to mod Z, and thus real of Z1 Z2 bar is less than or equal to Z mod of Z1 Z2 bar, and that now I shall write here. See, this is what is Z1 plus Z2 whole square, mod of Z1 plus Z2 whole square, and therefore mod of Z1 plus Z2 whole square will now be less than or equal to mod Z1 square plus, and this we are replacing 2 times real Z is replacing by mod Z, means real Z1 Z2 bar is replaced by mod of 2 times mod of Z1 Z2 bar. See, this quantity is replaced by the absolute value of Z1 Z2 bar, twice absolute value of Z1 Z2 bar, and plus Z2 bar mod Z2 whole square as it is. So first and last term is written as it is, and this real part of this complex number is less than or equal to absolute value of this complex number, and that is written. So using, or we may write the reason, since real z is less than or equal to absolute value of z. And but now you see what is the right side. Again, that can be simplified. The right side will be, now this is equal to, this right side is equal to mod z1 square plus, now it is 2 mod z1. This is again by this mod z1 z2 is equal to mod z1 into mod z2. So this will be mod z1 mod z2 bar and plus mod z2 square. And but again mod z2 bar is equal to mod z2. Absolute value of a complex number is equal to its conjugate, absolute value of its conjugate, and therefore this will be z1 mod z1 square plus 2 mod z1 mod z2 plus mod z2 square, since mod z2 bar is equal to mod z2. And but what is this? This is exactly the square of mod z1 plus mod z2. But what is the, this is equal to this expression, but what is the relation between the left expression and the right? Is this one, less than or equal to, and thus we have mod z1 plus z2 square is less than or equal to. Therefore this is less than or equal to, the right side is mod z1 plus mod z2 whole square. Now we take the square root on both sides and note that the absolute value is never negative, we get the relation. And so therefore mod of z1 plus z2 is less than or equal to mod z1 plus mod z2. This proves the property which is known as triangle inequality. Why it is known as triangle inequality? Because we have seen earlier z1 bar, mod of z1 represents length of vector z1, and we have shown the sum of these two vectors also. See, if this is a complex plane and if this is vector z1, if this is vector z2, then you see this is z2. What is their sum? Their sum is obtained by completing this parallelogram, because this will be z2 and this will be z1. So this is the sum, z1 plus z2. So thus this will represent three sides of a triangle. This is z1, this is z2, and this is z1 plus z2. Or that means the length of this side is mod z1, length of this side is mod z2, and length of the third side is mod z1 plus z2. And thus any one side of a triangle is, the length of one side of a triangle is less than or equal to the sum of length of the other two sides. That means sum of lengths of two sides of a triangle is always greater than or equal to the length of the remaining side. So because this represents the direct distance between 2 points by straight line, and this is via the point here, the third point is there, and therefore mod z1 plus mod z2 is always greater than mod of z1 plus z2. And when the equality is possible, all the 3 points are linear, collinear, then the equality will possible. If this is z1, this is z2, then z1 plus z2 will be this one. And so therefore this inequality is known as triangle inequality. Now one more result we shall see is mod of mod z1 minus mod z2. Absolute value of mod z1 minus mod z2 is less than or equal to absolute value of z1 minus z2. Now this is easy to prove. So we can write mod z1. Mod z1 is equal to mod z2 minus z2 plus z1 minus z2. So we have added and subtracted z2. So and we can group now this like, and thus this can be written as mod z1. This is using the triangle inequality, less than or equal to mod z2 plus mod z1 minus z2. Now we shall subtract mod z2 from both sides, or we shall shift this mod z2 on left side, and that gives mod z1 minus mod z2 is less than or equal to mod of z1 minus z2. And similarly, now we are interchanging the roles of z1 and z2. We get mod of z2 minus mod of z1. Interchanging z1 and z2 is less than or equal to z2 minus mod of z2 minus z1. But mod of z2 minus z1 is same as mod of z1 minus z2. See, there this result is also there, that is mod z is same as mod of negative z. Because by definition itself, this is root of x square plus y square, and this will be root of minus x whole square plus minus y whole square. Both will be the same. And now what we will have is this as 1 and this as second result. Now you see, this mod of z1 minus z2 is less than or equal to the right side, mod z1 minus z2, and mod of z2 minus z1 is also less than or equal to the same expression, and that means the positive value and negative value both are less than this quantity. So what is this? This is a negative of this one. z2 minus z1 is negative of mod z1 minus mod z2, and that is also less than or equal to mod z1 minus z2. And what is the first result? Mod of z1 minus z2 is less than or equal to mod of z1 minus z2. And or otherwise we have the result like this: a is mod a, or a quantity a is less than or equal to b, and negative of a is also less than or equal to b. So what this together imply? Absolute value of a is less than or equal to b. So that is the meaning, and therefore the absolute value of this expression is less than or equal to mod of z1 minus z2, and that combining 1 and 2, or from 1 and 2, we get absolute value of mod z1 minus mod z2 is less than or equal to mod z1 minus z2. So this proves the fourth property, and thus we have seen some properties of moduli. Now we shall solve some problems. I have written first problem here. Use properties of conjugates and moduli to show that these two results. Now we shall first solve the first problem, and here we have the left side is 2z bar plus 5. See, please distinguish between 2 and z. 2z bar plus 5 into under root of 2 minus I. This we can write like this, using the property of modulus. Mod of z1 into z2 is mod z1 into mod z2, and this is to be written as 2z bar plus 5 mod of 2z bar plus 5 into mod of root 2 minus I, and I shall suppose this as 1. Now again we shall simplify this separately. So we have, or that can be simplified by the same way here without taking separately. what we shall do is, this is equal to, this is mod of 2z bar plus 5 conjugate of it, and this I shall write root mod of root 2 minus I as it is. This for the time being we have written as it is, only this is changed. Why this can be changed? Because we know mod z is equal to mod of conjugate z, so we have taken conjugate of it, and now this is equal to, so what is the conjugate using the property of conjugate? See, conjugate of z1 plus z2 is conjugate of z1 plus conjugate of z2, and for that we can write this as conjugate of 2z bar, and this is mod of conjugate of 2z bar plus conjugate of 5, and this is as it is, and again this is equal to see mod of z1 z2, conjugate of z1 z2 is conjugate of z1 conjugate of z2. So this will be conjugate of 2 into conjugate of z bar, but double conjugate is same as z. Double conjugate of z is equal to z, and 2 is real number, conjugate of all real number is equal to itself. So conjugate of 2 is 2, conjugate of 5 is 5, and therefore this is absolute value of 2 into z plus 5. And what is the modulus of root 2 minus I? And that is under root of by definition of modulus of x plus iy, under root of real part square, that is root 2 square, plus imaginary part square, that is minus 1 square. And you see this is exactly root of this root 2 square is 2 and minus 1 square is 1, 2 plus 1 is 3, so it is root 3 into mod of 2z plus 5. So what is the result is here, root 3 into mod of 2z plus 5, and thus we have established the first result, easy to solve. Now the second is very easy to solve, only expand this, square it, and then take the conjugate, which will be equal to this one. So for second, try yourself. See, problem for practice. Now we shall consider the second problem. I have written here the second problem. Sketch the set of points determined by the condition. First, and this is the second. So actually two problems are there. We shall solve the first one. See, we have 2z bar plus I, mod of 2z bar plus I. We shall simplify this first. See, we have mod of 2z bar plus I, and we shall use the same property that we have used in our earlier lecture, earlier solution, and that is since mod of z is equal to mod of conjugate z, and that is 2z bar plus I, its conjugate, and this further can be simplified as using properties of conjugate. Conjugate of 2 is 2, and double conjugate of z is z, and plus, or we can write like this, plus conjugate of I, separating the conjugates, and this is now mod of 2z, so this is 2z because double conjugate of z is z, and conjugate of I. What is conjugate of I? I is 0 plus I, and conjugate of 0 plus I is, see, it is conjugate, and we have to change the imaginary part sign, so 0 minus I, which is minus I, and thus it is minus I, and therefore the expression on the left side is mod of 2z minus I, and so the given equation is, the given equation or condition here is becomes, now I shall write here. This is mod 2z minus I and is equal to 4. We have simplified this and obtained this as 2z bar plus I is equal to this one, 2z minus I. And now we can take 2 common from the left side, and then this can be written as 2z minus I divided by 2 is equal to 4. And this 2 can be written outside the modulus sign, and we can divide both sides by 2. So therefore this gives z minus I upon 2 is equal to 2, dividing both sides by 2. So thus the equation we have expressed in this form. And now what is the use of this? Because that is a standard relation we have seen earlier. We know that mod of z minus z naught is equal to r. What this represents, we have seen it earlier, represents a circle with center at z naught and radius r, because the left side is distance between z naught and z, and that distance is equal to r, means it is a circle, all the points which are at a r distance from z naught, and that is a circle with center at z naught, radius r. So comparing these two equations, the equation 1, therefore the given equation, or that can be written as this is the given equation. So this equation, therefore the given equation represents a circle with center at this point z naught, that is minus I by 2. And this complex number can be represented in complex plane as 0, minus half, because it has real part 0, imaginary part is minus half. Center at this point, and radius is 2. Now we are asked to sketch this, and that means we can draw the figure like this. So it is a circle with center at this point. Zero minus half. Suppose this is 1 unit, and this will be half, and this will be half unit, and this is minus half, this will be 1. So center is 0 minus half, and that will be on the y-axis. Whether we have expressed it correctly, center at z minus I by 2. So it is 0 minus half, and that means center will be this. Center will be this point on y-axis. The center is on y-axis, and the radius is 2. So radius is 2 unit. So this is half unit, and this 1 unit. This is the radius, and therefore it will be a circle. So there is a mistake. You see, it represents a circle with center at plus I by 2, not minus I by 2, because what we have is z minus z naught. Mod of z minus z naught is equal to r, represents a circle with center at z naught. So no negative sign is to be taken, and therefore it is a center at 0 half, and therefore center will be at this positive y-axis. So if this is 1 unit, center is at half, 0 half. This is the center, and radius is 2. So this much is the radius, 2 unit. This will be 2, and then this is 1 unit and half unit. So this is 1, and therefore it will represent a circle with center at this point, 0 half, and radius is 2. Radius is 2. So this is the sketch for the equation. It is a circle. No interior point will be there, but the points on this circle will be represented by the first equation that we have seen. Now the second, this is easy, and you should solve it. Real part of z minus I is equal to 2. The answer, try yourself. The answer is x is equal to 2. You simplify, this will be simply x. X is equal to 2, and x is equal to 2 is a line parallel to y-axis passing through the point 2, 0, and easy to draw that line. So this will be x is 2, and that is the line, x is equal to 2. So this is the only sketch for the second. You solve yourself. I hope you will understand this part, and the remaining we will continue in our next lecture. Thank you for watching the lecture.